So today we're going to go over the basic units of physics and one-dimensional and two-dimensional motion. So firstly, to start off, vectors and scalars are the basic units of physics. And vectors have magnitude and size as well as direction, while scalars only have magnitude and size. So which means that vectors have a positive and a negative direction, while scalars is like an absolute value that only has a magnitude and a size, or a positive number, because magnitude and size cannot be negative. Vectors can also be added, subtracted, or decomposed. Firstly, to show the addition of vectors, this vector right here would be the vector of A plus B, because it starts off with here and it follows the vector A till here and ends with vector B. So the blue vector right here would be the vector A plus B. On the other hand, when we look at the vector subtractions, that would be vector A minus vector B, and so on. Lastly, this composition of vectors is basically dividing a vector into two different components. And we mainly divide a vector into an x component and a y component. And just like the x-axis and the y-axis, you can divide it into two components. And assuming that that's theta, this would be the x component, and this would be the y component of this vector A. And then the x component would be A cosine theta, and the y component would be A sine theta, due to trigonometric identities. So next, moving on to how to calculate the average velocity and the speed. Firstly, distance and displacement are two different concepts. So starting with distance is basically how much someone or an object has traveled in total. Starting off with distance, if a person has moved, for example, 3 meters up diagonally, 4 meters to the right, 3 meters back down diagonally, and 4 meters back to the left, and ended at the same spot, the person would still have moved 3 plus 4 plus 3 plus 4 meters, which is 17 meters. On the other hand, displacement is how much a person or an object have moved since the very beginning. So if the person or an object have moved 3 objects to the right, to up diagonally, and 4 meters to the right, 3 meters back down, and 4 meters back. Although the distance this object has moved would be 17 meters, the displacement would be 0, because the person came back to the same spot the person has started. So the displacement would be 0. And so here we can realize that a distance is a scalar factor, while a displacement is a vector factor, which means that displacement has direction, while distance can only be positive, because you can never go negative distance. While there can be negative displacement if you set the right side as positive or left side as negative, if you move to the negative direction, your displacement would be negative something. So that's something to keep in mind. Next is velocity versus speed. So here in the graph, there is a position time graph drawn, and assuming that this point right here is point where point t1, x1, and this point here is t2, x2. And if we draw a little triangle right here, we can know that the velocity is change in x over change in t. I just use this triangle notation as delta, which basically means change. So this would be equal to change in x would be equal to x2 right here minus x1, because that would be the change in x. So I wrote x2 minus x1 right here. And the delta t would be right here, which is t2 minus t1. So that would basically be the velocity. So to sum it up, the average speed is distance over time, where average velocity is displacement over time. And something to note here is because displacement is equal to time times velocity, we can find the displacement by using a velocity time graph. So assuming that this is a velocity time graph, the area of this square would be the displacement. In this case, it's really simple to find the displacement, as you can just multiply x by y and you get the displacement. On the other hand, there are some instances where you get a graph that looks something like very curvy. And in this case, to find the area and therefore to find the displacement of this velocity time graph, you'd have to use integrals to find the area under a curve. So moving on to an example, if t equals 1 and a person travels from point A right here to point B, what would the average speed be? So as I said, speed is distance over time. So the distance a person has moved from A to B in a semicircle would be half the circumference, right? So that would be, the circumference would be 2 pi r, and half of that would be 2 over 2 pi r would be the total distance this person have moved. And because we assumed that time is 1, time would be 1. So that would equal to pi r. So the average speed of this object or person would have been pi r, meters per second. And average velocity is displacement over time. And therefore, the displacement is only, although the person has moved through this path, the displacement itself is only 2r because the person has technically only moved that much. So the displacement is basically the distance. When we talk about distance in math, you generally consider the notion of distance as the shortest pathway from point A to point B. And that's how we consider displacement. So the displacement would be 2r over 1. So note how an average speed and an average velocity can be very different due to the definitions of them. So next, we're going to move on to acceleration. Acceleration is essentially the rate of change, and the rate of change can be equal to slope. In this graph shown, the acceleration would be change of velocity over change in time, which is v2 minus v1, because change in velocity is right here, which is v2 minus v1 would give us this distance. So v2 minus v1 over, we need to, when we're finding change in t, it would be this much of the region, which would be t2 minus t1. So therefore, it looks something like this. And that'd be the acceleration. Next, we're going to move on to the position time graph, velocity time graph, and acceleration time graphs. So these three graphs are interchangeable. I mean, we can go from one graph to another easily when we think of the notion that velocity is the slope of the position time graph and the acceleration time graph is the slope of the velocity time graph, essentially. So here, when we look at this graph right here, because it's a linear position time graph, the slope is positive, and so the velocity time graph would look something like that. And because acceleration time graph is the slope of velocity time graph and the slope here is 0, the acceleration time graph would look like that, basically meaning that there is no acceleration. Next, if this is a position time graph given, the slope would be decreasing, so the velocity time graph would look something like this, and therefore the slope here is also negative, so the acceleration time graph would look something like that. And here, when we're given the velocity time graph, we can also reverse and go back to finding the position time graph. And here, because the slope is always decreasing, but is positive in the first half and gets negative, the position time graph would look something like that, like a semicircle. So the slope is decreasing, but it's still positive until halfway, and it's decreasing from there on. And the slope of this is still negative, so the acceleration time graph will look something like that. Now we're going to move on to one-dimensional motion. So these four equations shown are the kinematics equations. And the kinematics equations are the building blocks of how to solve one-dimensional motion and even two-dimensional motion physics problems. So they're very handy to keep in mind and even memorize them. So the V here means velocity, and VO means initial velocity, and A means acceleration, and T means time, and delta X means basically the distance. So the first typical type of one-dimensional motion is a free fall, and in a free fall, the velocity is not always constant, as the acceleration is the gravity, right? Because in a free fall, there is only one factor that can affect the velocity, which is the gravity, and that would also be the acceleration in this case. And the initial velocity would be 0, because in a free fall, you would technically drop an object. So at that moment when you're dropping the object, the velocity would be 0, because you're just releasing it from your hand. And from here, these two components, we can derive 3 equations based on the kinematics equations above. So from the equation V equals VO plus AT, because we know that VO is 0, we know that that's 0, and we know that acceleration is g, we can know that in a free fall, not in all cases, but in a free fall, we can know that the velocity is the gravity times time. And we can also know that distance is 1/2 gt squared, because when we're looking at this equation above, the VO is 0, so that would cross out, right? So that's another equation we can derive. And the last equation we can derive is V squared equals 2GD. Next, moving on to throwing upward. So the throwing upward motion is very similar to a free fall, as the second half of where the ball comes back down from this from the point where it hits the highest point, it's the same motion as a free fall. But while it's going up, that would be the reverse motion of a free fall. So here the acceleration would be the gravity, because while the ball is up in the air the entire time, the only acceleration it has is the gravity, right? So from this factor, we can derive 3 equations, which is V equals V initial minus GT. That's the equation derived from this equation right here, and we replaced A with G. And by the same logic, we can do D equals VOT minus 1/2 GT squared, and V squared minus V initial squared equals minus 2GT. So these equations are only applicable when the motion is throwing upward. Now moving on to the two-dimensional motion. The first one would be throwing horizontally. So in this case, you'd be throwing a ball horizontally, and because the ball is being released, it would drop, but with the projectile motion. So we can divide this motion in 2 different components. And the first component is the vertical component. And the vertical component of a motion of a ball that's thrown horizontally is basically a free fall. And the horizontal motion of the ball that's thrown horizontally is a motion that has constant speed and no acceleration. And building up upon that horizontal motion, there's a projectile motion. And in a projectile motion, it's usually a ball being launched at an angle. That's what we usually call a projectile motion. In a projectile motion, if a ball, in this case, if a ball is launched up in that direction, that would be the initial velocity, right? But here, assuming that that's theta degrees, because we know based on our trig identities, the velocity of the x component would be v initial times cosine theta. And with the same logic, the vertical component of the initial velocity would be VO sine theta. And based on these facts, we can derive a few equations that give us a pretty good insight into calculating the range and the time and the height. Okay, so that's basically from this equation is from the equation that says v equals v initial plus at. And I just, these y's and f equals final velocity, and this y equals the y component of it. So from this, we're going to find the time. And we're going to find the time when we're finding the time of a projectile motion that goes like that. We're going to consider that point A and point B at this highest point and point C when it lands. So firstly, we're just going to consider the time it takes for the ball to go from point A to point B, since it's equal motion from A to B and B to C. So the final velocity when the ball reaches point B would be 0. And the initial velocity would be, because we're only considering the y component, it would be v. So 0 equals v sine theta plus acceleration would be, as I have been mentioning multiple times, because when the ball is in the air, the only acceleration is gravity. The acceleration here would also be gravity times time. So we're trying to isolate t, and we get minus v sine theta equals gt. And therefore, t equals 2v sine theta over g. And the reason why I put 2 is because that is basically the time it took from the ball to go from point A to B, and we need to times by 2 in order to get the full time from the ball when it leaves point A to when it reaches point C. Next, we're going to derive the height. So here, the same logic, the final velocity when the ball reaches, because the height would be this part, so that's the height. So the final velocity would be when the ball reaches point B, which is 0. And then the initial y velocity would be v sine theta squared plus 2a is g, like we have been mentioning, 2g, and dy would be how much the ball has traveled vertically, which would be height. So here, when we isolate h would be h equals v squared sine squared theta over 2g. That would be h. So from these two derivations right here and right here, we can derive the range of a projectile motion. And because we know that the range, which is how far it has traveled, delta x equals vxt. And the vx would be the velocity of the x component, which is right here, vo cos theta. So it would be vo cos theta times time. And the time is equal no matter the component is vertical or horizontal, because the time it takes for a ball to move from point A to point C is equal no matter we're considering the vertical component or the horizontal component. So we can plug that time in right here, which will give us v cos theta times 2v sine theta over g. And if we simplify that, we'll get something like v squared 2 sine theta cos theta over g. And because from our trig identities, we know that that part is equal to sine 2 theta, we can get an equation v squared sine 2 theta over g. And that's our range. So from this derivation, we can find a formula for the range, and from here we can figure out the maximum range. And in order to throw a ball with a maximum range, we can figure out that we have to throw the ball in a 45-degree angle because gravity stays constant, right? And the velocity also stays constant. So we're trying to maximize this sine 2 theta. In order to maximize sine 2 theta, the maximum value of a sine something angle is 1, because sine 90 degree is 1. So theta would have to be 45 to maximize the range, assuming that we're throwing under the same condition with the same initial velocity.